Right now, as you watch this, your body is doing something almost unbelievable. Every single day, you produce and use up roughly your own body weight in a single molecule. If you weigh 70 kilos, that's about 70 kilos of it, made and spent every day. And yet, at any given moment, you're only carrying about 60 grams of it, which means each molecule gets used and rebuilt once or twice, every minute. The molecule is called ATP. And here's the strange part. The food you eat never actually becomes your energy directly. It has to be converted into this first. This is what that constant renewal looks like. Not a static reserve you draw from, but a ceaseless river of molecules, built, spent, and rebuilt, without pause, in every cell you have. To keep you alive, your body synthesizes and consumes ATP on a scale that's hard to even picture. It never stops, not for a single second of your life. So what is it? ATP stands for adenosine triphosphate, and the name tells you the whole structure. There's adenosine, that's a base called adenine attached to a sugar. And then there's the important part, triphosphate, 3 phosphate groups, linked together in a tail. That tail is where the action is. Each of those phosphate groups carries a negative charge, and negative charges hate being close together. They push against each other, hard. So this little tail is packed with tension, like 3 magnets forced together the wrong way. Hold on to that image. It matters in a second. Now, here's where almost everyone gets it wrong, including a lot of textbooks. You've probably heard that ATP stores energy in a high-energy bond, and when that bond breaks, energy is released. That's not really true. Breaking a bond always costs energy, never releases it. So what's actually happening? When the last phosphate is snapped off, with the help of a water molecule, you get ADP and a free phosphate. And those 2 products are far more stable, far more relaxed than the tense molecule you started with. Those crowded negative charges finally get to spread apart. The products settle into a lower energy, comfortable state. And that difference between the tense before and the relaxed after, that's the energy the cell gets to use. It's not stored in the bond. It's released by the whole reaction, finding a calmer place to be. So if ATP gets used up, why don't we run out? Because it's rechargeable. Once ATP becomes ADP, the cell can add that phosphate back on, reloading the tension, rebuilding the currency. But that costs energy. And that energy comes from your food. This is the real reason we eat. Not to get energy directly, but to recharge this molecule over and over. Which brings up an obvious question. Why go to all this trouble? Why not just burn the food and use that energy straight away? And the answer is one of the most elegant ideas in all of biology. Think about money. You don't trade a cow directly for a loaf of bread. You convert the cow into currency, and that currency can buy anything. ATP is exactly that. Burning food releases a huge, messy amount of energy. Too much, too fast, in the wrong form for most jobs. So instead, the cell packages that energy into small, standard units of ATP. And almost every energy-demanding job in your body, moving a muscle, firing a nerve, pumping a molecule across a membrane, is paid for with the same currency. The cell couples them. It links a reaction that needs energy to the release from ATP. So the 2 happen together. One universal currency, millions of different transactions. And here's the part that gets me. This exact molecule, same structure, same phosphate tail, isn't just yours. It powers bacteria. It powers plants, fungi, fish, elephants, the mold on old bread. Every known living thing on Earth runs on the same currency. Not a similar one, the same one. Which means ATP was almost certainly being used by the single ancestor all life descends from, more than 3.5 billion years ago. Life has changed almost everything since then, but it never replaced its money. So why this molecule? Why did life pick ATP out of everything it could have used? And honestly, we don't fully know. Maybe there was something chemically special about it, something that made it the natural choice. Or maybe it was just the version that happened to work first, got locked in, and became impossible to replace once everything depended on it. A frozen accident, 3 billion years old. We can't yet say for sure. And that gap, that's not a failure. That's one of the most interesting open questions in biology. So that's the currency. Now the real question is, how does your body actually make it? How does a single molecule of sugar get turned into usable ATP? That's where it gets beautiful. And it starts with a process called glycolysis. That's the next episode. If this made the invisible machinery inside you feel a little more real, stick around. We're just getting started.